Hello, my name is Scott Grizzard. This is Calculus 1 for Fall 2020. I'm from the University of South Florida. And tonight's lecture is 8B. It was the lecture that was supposed to happen on last Thursday before I didn't show up. So we're doing that lecture today. Today we're going to be talking about inverse functions and inverse trigonometry. As usual, if you are in my class, there's class chat in Discord. There's also class chat in, you can also ask me questions on Twitch, off to the side there, but please remember that Twitch questions are public. Okay. So what we want to do is so the next module is module 3. And module 3 centers on the idea of concavity, convexity, and optimization, minimum and maximum, that sort of thing. But there's a little bit of cleanup that we have to do, something that probably should have been in module 2, but it just kind of left over. So we're going to do that tonight, and that's this inverse function stuff and then the inverse trig. We may finish inverse trig tonight. It may be, and then, so tonight's lecture is on Sunday instead of last Thursday. There will be one tomorrow, as usual, for the usual Sunday, which will be 9A. Any other announcements? The website is now up. The quiz for tomorrow, of course, is the usual survey quiz. It's up. The other announcement to make is that those nice notes that I've been posting in Canvas, I'm out of those. So obviously these notes that we do tonight here will be posted, but I'm out of the nice typed ones with all the beautiful type definitions. Every year I push them forward. Every semester I make some more nice ones, and I'm now out of the ones I've made. I've about halfway done with tonight's, what would be tonight. But the nice notes, there are a couple from Module 4, but the nice notes are pretty much, I'm out of those. Hopefully I'll get one or two more up this year. And then, of course, next semester I'll have those and then one more. So, but yeah, so the nice notes go through modules 1 and 2, and there are a few in module 4, and hopefully there'll be a few in module 3 that I finish. Anyway, let's go ahead and start with what we want to talk to about tonight. So tonight, again, we want to talk about inverse functions and inverse trig. And on WebAssign, you all have already seen this inverse function on a pre-calc review. If you haven't done that pre-calc review, go ahead and request an extension. And you can do all this idea of an inverse function. And the book wants to emphasize the idea of a one-to-one thing. But there's a little bit more to it than that. And there's a little bit of nice math in here that really helps you understand what's going on behind the scenes. So let's start by talking about that. Okay. So we've got this idea of a function from before, right? I've got some kind of x space here. And I've got a y space here. And so let's for the moment, let's let the x space, let's let x equal a, b, c. And let's let y equal 0, 1, 2. And then I've got this, so I've got a nice finite function here. You know, I've got two nice little finite sets. And let's let f be the function, be the following function. So f is going to map here. Here's a, here's b, here's c, here's 0, here's 1, and here's 2. And f is going to be this nice little function that maps a to 1, b to 0, and c to 2. So f equals the function a1, b0, c2. So recall that a function is a set of ordered pairs, right? So recall. Let f be a set of ordered pairs from x cross y. It's supposed to be x little x times y. It's not erasing again. All right, so let x and y be sets. F be a set of ordered pairs from x cross y. F is a function. Let me see if I've got this already typed up here. Yes, I do. So I'm just going to use this nice little statement right here. That's a little better. I didn't mean it to be quite that much. I also didn't mean it to have I didn't mean for it to have, excuse me for a second. I didn't mean for this thing to exist. There we go. All right, so I had this definition that f was a function if colloquially every x was used and no x was used more than once. Right, so this is a function. And I could also write this function as f goes, let's see. If I wanted to write this in rule notation, f of x equals, and then I've got 3 piecewise, 0 if x equals b, 1 if x equals a, and 2 if x equals c. And it should be noted that this a, b, c are not like constants or something. Those are the actual objects in x. The x doesn't always have to be numbers. Okay, so how do we feel about this concept 1 to 5? I've got a function. It's got some properties. But it's just it's a finite function, and the polling system's not working, so you guys are just going to have to type it in. Sorry about that. So 1 to 5, how do we feel about this? Okay. All right, now the question is, how do I go back? Okay. So the question is, how do I go back? Okay, so I'm going to let G, I'm going to define G, and notice that G is going to take values from Y and go back into X. Okay? And I'm going to do it as the following. So what I'm going to do is I'm going to send 1 to A, 0 to B, and 2 to C. So I have the set of ordered pairs 0b, 1a, and 2c. And notice that g is a function. It's a function from y to x, but it's still a function, right? I go, every x x's in this case are y's. Every first coordinate is used, and no first coordinate is used more than once. Okay, so 1 to 5, how do we feel about this idea that f is that g is a function? Okay. All right. So let's do a little definition here. Definition. Okay. Let x and y be sets, and f be a function from x into y. Let g be a function from y into x. So I have this situation here where I have an x space, where I have an x and a y as sets. I have this f going this way, and I have this g going this way. Okay. G is the inverse of f if two things have to be true. For every x in x, g of f of x, g of f of x equals x, and for every y in y, f of g of y equals y. Okay, so now let's look back at our example. Okay? G is the inverse of f if for every x in x, g of f of x equals x. In other words, if I start here at c, right? C is an element of x. I'll go to 2 with f of x, and then I go back to c. So back in our example, right? G of f of c equal g of 2 equals c. G of f of a equal g of, okay, so I took a to 1, and then g takes 1 back to a. G of, that's right behind my head, right? G of f of b equal g of 2, because f took b to 2, and then g took it back. I'm sorry, f of b was g of 0, and then it took b back. Okay, so that first condition is met. The second condition says that I can also go this way and then back. So f of g of, in my condition here, f of g of 0 equaled equaled f of, so g took 0 to b, and then f took b back to 0. F of g of 1 was f of a, and then a went back to 1. F of g of 2 equaled f of c equaled 2. So it's got to work both ways. 1 to 5, how do we feel about that definition? Okay. Well, let's do another example. Okay, so let's let R be both the consider x cubed from R to R. Okay? And we'll call this x to y. And this x is R and y is R. So I'm going to and from the same set. And the square root of the cube root of y from y to x, even though both of these are R. All right. So if I have x cubed here, all right. Not drawn to scale, of course. I actually want to talk about what's going on in here. That's why it's not drawn to scale. Okay, so where does x cubed send 0? Okay, well, 0. And the cube root is going to send it back. Likewise, 1/2 goes down to 1/8. And then this sends 1/8 back to 1/2. 1 goes to 1. And back to 1. 2 goes to 8. And back to 8. And on this side, the exact same thing happens, right? Okay, so 1 to 5, how do we feel about that? Okay. All right. Now, every function doesn't necessarily have an inverse, right? So consider this function. Consider f from R to R, where f of x equals x squared. Does f have an inverse? Okay. Let's look at these things. So here's 0, 1/2, 1, 2, 3. I needed more space. 2, 3, 4. 1, 2, 3, 4. Negative 1/2. Negative 1. Negative 2. Negative 3. Negative 4. Negative 4. Negative 3. Negative 2. Negative 1. Negative 1 over 2. Negative 1 over 4. Negative 1 over 4. I don't care about the others. All right, so the question is, do I have an inverse? Well, let's see. Kind of the same situation here. 0 maps to 0. That's all hunky-dory. 1/2 will head to 1/4. Shouldn't be a minus there. One maps to 1, 2 maps to 4. But now when I go over here, what happens? Well, negative 1/2 maps here to 1/4. Negative 1 maps to 1. Negative 2 maps to negative 4. So if I wanted to find an inverse, where do I go back again? Right? And also, how do I get from negative 1? The second, if y equals negative 1, there is no to go back to. 1 to 5, how do we feel about those two problems? Yeah, still doesn't work. 5 pole still doesn't work. So now I've got two problems, right? I've got, if I want to get somewhere, if I go to 1, I don't know how to define the going back. And I can't get there from here. So this does not have an inverse. Okay, we've run into two problems here. Now, note that I could fix it. by messing with these two sets. So I can fix it if I restrict F's domain and its target. Okay? So let's redefine it. Let's define a new set. So if F goes from, okay, here it's obvious that the negatives are the problem. The negatives are the problem here in the domain, because if I could get rid of the negatives, I wouldn't have this problem of sending stuff back, right? Because then, if I got rid of the negatives, well, 1 would map back to 1. Because without a negative 1 mapping to 1, it's unambiguous where 1 should go. Likewise, my other problem is that there's no x to go back to. Actually, I can fix that, right? I just chop off this little set here. I chop off the negatives in y, and now I've got places to go back to. So if f was defined from 0 infinity to 0 infinity, I wouldn't have a problem. So I'm going to call that f star. So f star of x equals x squared, right? But is undefined for x less than 0. Is everyone on board with that? F of 1 equals 1. F of 2 equals 4. I'm sorry, f star of 1 equals 2. F star of 2 equals 4. F star of negative 1 is undefined. How do we feel about that? I can't define it, because if I could define it, I wouldn't have an inverse. So, g of x equals the square root of x is not an inverse for f. But it is, but g is an inverse for f star. Okay. So how do we feel about that one? 1 to 5. I'm not seeing any voting going on here. Probably because nobody's watching. Oh, a few people are. Okay. Excellent, excellent. All right, so let's think about it. Let's give this thing some properties, right? We're going to call this. So let's let x and y be sets. All right, so let's do some definitions here. Let x and y be sets. All right. And f, a function, x to y. F is onto, that's the word, if for all y in y, there exists x in x so that xy is in f. In other words, every y is used. F is, second definition, 1, 2, 1, if for any two distinct points, x naught, y naught, oops, I want indent, x1, y2, sorry, y1 in F, y's naught does not equal y1. In other words, no y is used more than once. Okay? So compare this bit to our original definition of a function, right? Here, every x needed to get used. Here, every y needed to get used. Here, every y needs to get used. And here, every y needs to be used more than once. Okay? So let's do some examples. F from R to R, f of x equals x cubed is both 1 to 1 and onto. G from R to R, so that g of x equals the square root of, I'm sorry, nope, that's not defined on R. Let's see, g of x equals tangent of x is onto, but not 1 to 1. So let's see what that looks like. So the tangent of x here, you see here, it's going to hit every pi. It's going to run over all of the real numbers, right? So it is onto. You know, if you give me a real number, I can get there, right? You give me, the y's are all taken care of. You give me 4, and I can find you an x that will get me to 4. If you give me right, I can actually find several x's that get you to 4. But for any natural number you give me on this y-axis, I can find somebody there. 1 to 5, how do we feel about that? Sorry, the thing is like kicking back on my... Okay, there it goes. All right. So what I want... Can somebody give me an example of a function that is 1-to-1 but not onto? Anybody? Well, let's go back to our old friend here. Let's consider h from 0, infinity to r, so that h of x equals x squared. Now, notice I'm 1-to-1. Since I've excluded the negatives from the domain. But I still do not reach the negative numbers that are part of the codomain. How do we feel about that? 1 to 5. Okay. All right, so I've got a big theorem here. And intuitively, this is obvious, okay? Here's the big theorem. If f is both 1-to-1 and onto, then f has an inverse. Now, like many things that are intuitively obvious, this particular theorem is a pain in the neck to prove. So we won't be doing it. It requires you to have, in order to do it for infinite sets, it actually requires the axiom of choice, which is far beyond our the scope of this class. But you can see intuitively how this is true. Okay. All right, before we go into fixing functions, which we've already kind of previewed here, let's talk real fast about f is 1-to-1, then f is an inverse. I just totally lost my train of thought. Okay, so we've got this idea here. Now, before we go into let's just go in, let's do... I totally forgot what I was going to do. Let me see my outline. Yes, okay. So, let's go into these trig functions, because they're the ones we want to look at. Okay. So let's look at the trig functions, particularly let's look at sine. So sine of x is defined, so sine is a function. Oh, let's look at the notation. Sorry, that was the thing I wanted to do first. A note on the notation. So notation for inverses. And this is a major warning here, so I'm going to give you a warning. Okay. F, let G be the inverse of F. Then G is commonly written as G equals F to the negative 1. All right, so this is this negative 1 notation. And here's the annoying bit. This thing is abused everywhere. So there are a couple things to watch out for in this notation. First, F to the negative 1 does not mean one over F. Okay? F squared means F of X, not F of X times F of X, unless F is a trig function. Okay? Sine negative 1 is not actually means the inverse of sine, even though sine does not have an inverse. We will get to that. Okay? And here's the big thing. Sine negative 1. I'm going to write this in like the blood dripping. Isn't there like, yeah, the blood dripping pen. Sine negative 1 of X is not 1 over sine of X. Okay? Sine negative 1 of X equals arcsine of X. Okay? This is confusing and horrible and I don't know what else to say. Stinks. And mathematicians hate you. Okay? Not you in general. I mean, you in particular there in chat. And, you know, we're just fair. Right? This is horrible. Sine negative 1 is not 1 over sine. 1 to 5. How do we feel about that? Okay. So this is like the big warning. If you get nothing else from this lecture, I hope you take more. But please don't confuse these two. The big warning. It's there in blood. Okay. I will try to avoid I can't stop others from using it. I can't stop WebAssign from using it. I can't stop the book from using it. I think it's a horrible thing. I think that I think this is one of the things that is the reason why so many people hate math, is this notation, but it is what it is, and we're stuck with it. As I said, I will try not to use it, but I can't stop others from doing it. Okay, so sine of x. Okay. And I say inverse function, so we'll get to that in a minute. So sine has the following problem. Notice sine is neither 1-to-1 nor onto. Oh, by the way, this should be an if or only if. So this is supposed to be if and only if f is both 1-to-1 and onto. Notice sine is neither 1-to-1 nor onto, right? So sine of x has this nice little derivative. It has this nice little function here. It looks like this. Let's paste it in there. So if I tried to define an inverse for sine, right, I'd wind up with something that looks like, let's see, sine of y equals x. So if I tried to define an inverse for it, I'd wind up with something that wasn't a function. Okay, so how do we feel about that 1 to 5? Right? This is sine of x here. Right? And here's here's flipped, right? Here's sine of y. So here's x equals sine of y. And that's not a, right? That's not a function. So I've got a problem, all right? I've got a problem that this is neither 1-to-1 nor onto. Okay, how do I fix it? Okay. So how do I fix it? Well, the first is easy. So I've got sine. Sine is defined from all of r to r. And remember, sine asks the question, what's the northiness as I go around the unit circle? Okay. So the first is to restrict the target. Well, fixing onto is easy. So let's define sine star so that sine star is both 1-to-1 and onto. All right. So the first thing I'm going to fix is the obvious thing, right? I'm going to have sine star here, and it's going to be, I don't know what set I'm going to be from, but I dang, no, I'm just going to restrict the target to the range. And this is why your book doesn't talk about the onto problem, okay? The book doesn't talk about onto because it's something that's really easy to fix in calculus. It's harder to fix later as you move up, if you move up in the math sequence. So I'm introducing it now, but it's easy to fix right now, right? So I've got this nice little target of R, and now I just restrict it to its range. Right? It's going to hit everything between -1 and 1. So my sine star, which will have an inverse, is going to have a domain of -1 to 1. The inverse will have a domain of -1 to 1. Right? It's not going to have a domain of R. It's going to have a domain of that. But I've now fixed the onto problem. 1 to 5. How do we feel about that? That I've now fixed the onto problem. It's still not working. Polling is still not working. Okay. All right, so the next thing I need to do is I need to fix the domain problem. Well, the domain problem. I want to talk about parts of the unit circle, okay? There's some parts of the unit circle that are more valuable than others, right? Every point on the unit circle is equal, but some are more equal than others, right? So let's see. I can't take everything with me, right? Because if I try to take everything with me, I end up with this. So what should I take with me? I want the first quadrant. Some parts are more equal than others, right? Some parts of the unit circle matter more than others, right? So what I'm going to do is I'm going to choose, I'm going to take this bit here. I want that first quadrant. I want the values. I want 0 to 2 pi. I'm sorry, I want 0 to pi over 2. Is everyone on board with that? I want 0 to pi over 2. Right, I want positive acute angles. 1 to 5, how do we feel about that? I want positive acute angles. Positive acute angles. Okay, that's 0 to 90 degrees, otherwise known as 0 to 2 pi radians. Okay. I want these angles because these are the ones that I most commonly encounter. Okay. Obtuse angles are nice, right? But I want the acute positives. If I get nothing else, if I could choose nothing else to include, I'm going to want to include acute positive angles first, right? My first choice is not going to be the numbers from 0 to -2 pi or from 3 pi over 2 to 0. My first choice is not going to be this. My first choice is not going to be this quadrant here. Those are valid choices, but in one sense, they're just not quite as useful. Okay. I definitely want to be able to say the arcsine, the inverse sine of 45 degrees. I want 45 degrees in there. It's commonly done. I want that angle. Now, that's not to say that any other choice would not be valid. It would be as long as I'm 1 to 1 and on to. Okay? Now, the second thing is I want to have an unbroken domain. I want to have continuity. An unbroken domain. Okay? So what I mean by that is that when I do this, so if I have psi y equals x, where, let's see, where I restrict x to, so x is greater than 0 and less than pi over 2. Excuse me for a moment. I need to look up this thing. I did that. Oh, I have to put the equals, the thing equals, right? There we go. Okay, so if I restrict x to, pi over 2 is greater than x. No, other way around. Greater than, nope, just south. Work out all of these graphs ahead of time. Okay, so the portion that I'm going to have right now is this portion here. So this is the portion I'm committed to. Right here. Oops. There it is. So there's my first quadrant. Now, if I go any farther, okay, so let's say I decide to go to pi. So let's ditch pi over 2. And let's go to pi. If I go to pi, the problem is that now my function is no longer 1 to 1. Okay? I can't go to pi because then my function is not 1 to 1. Because then my function is not 1 to 1. I know you can't see that what I'm writing, but I'll show it to you in a minute. Okay, so I can't go to pi. What else can I do? Well, let's go for that third quadrant. So what would happen? Remember, sine is the northiness. Okay? So what happens if I choose instead this region? That will actually work, right? If I come back here and I say that sine is there between those and those things, and I put a comma here on Desmos because what I want to see is a broken domain. And then I say, I'm going to go for pi to 3 pi over 2. It'll work. So pi is less than x, is less than 3 pi over 2. And if that's the case, I still want sine of x. This needs to be pi over 2. Right? That'll work. If I chose the third quadrant, this would be my function. And that's okay. That would be a function. 1 to 5, how do we feel about that? I could do that. Yeah. I could do that. But do I want to? Okay? As I said, that's a valid choice. I'm going to make the screen go dark while I copy and paste that into the notes. That is a valid choice. Okay. Also valid would be to come here. Let's copy this sucker. Okay. Also valid would be this choice. If I chose the fourth quadrant, it would be 3 pi over 2 is less than x is less than 2 pi. And there's the jump. That would also be a valid choice. Right? That would be choosing the fourth quadrant. But it's still kind of broken. And I don't really like that. But what if instead I took this third choice let's modify it a little bit. But instead of going this portion of it, let's do this portion. Okay. Now I've got something a little different. Of course, this has got to be less than or equal to. Now I've got something a little bit different here, right? Now I've got that same choice. Now I've chosen quadrants 3 and 4. I'm sorry, I've chosen quadrants 1 and 4, just like I did before. But now I've got something with an unbroken domain. I just started in the negatives. Okay. So how do we feel about that, 1 to 5? So this function here, is what I'm going to do. Oops, the screen came up. That's what I'm going to do. I'm going to choose this portion of the unit circle here. Right? And I'm going to call that the portion I'm going to use. So now I've got sine star is going to go from negative pi over 2 to pi over 2. Right? And this is going to be its graph. For some reason, it's not letting me move the graph. There we go. And that's going to be its graph, and we're going to call that little function sine star. Now I do the following. Now I define. It's trying to reconcile two things, and I don't think it's going to like what just happened. This is going to be fun. Now I'm going to define the following. I'm going to define sine star of x here, and this definition says that x, this is going to map to sine of x, right? So it's sine of x, but it's just restricted. Okay. Now I'm going to define arcsine as the inverse of sine star, because sine star is now 1-to-1 and onto. Okay, so I could think of this. This is another way to think of it. I could think of sine star of x equaling sine of x if x is in negative pi over 2 pi over 2 and undefined otherwise. Okay. All right, well, how do I find the derivative of this thing? By the way, a cosine of x I'm going to define from, so cosine star is defined from negative pi to negative 1 to 1 in the same manner. Okay. Let's steal my little thing here. So here's it's not syncing tonight. I think there's too much traffic on the internet. There we go. So here's my graph for cosine, but I'm going to define cosine for the same reasons, but cosine's going to work from pi to 2 pi. So this is cosine of x. Cosine star. And arc cosine is going to be a function from negative 1 to 1 to negative pi. I'm sorry, not negative pi. This is wrong. From 0 to pi. All right. How do I take the derivatives of these things? I claim that I'm going to end this lecture by 8:20, and I claim I have enough time to do the derivative of sine, to do the derivative of arcsine. Okay. What I'm going to do is this. I am going to do... so I'm going to start my strategy. Implicit differentiation. Okay. Let y equal arcsine of x. Okay. Then sine star of y equals sine star of arcsine of x. Since sine star and arcsine are inverses, sine star of arcsine of x equals x. Right? That's part of the definition of being an inverse. Okay. Well, that's kind of nice. So thus, I've got sine star of y equals x. All right, let's take the derivative of both sides in terms of x. D over dx of sine star of y equals d over dx of x. Well, this one's going to end up being 1. Here I'm going to have a chain rule. So I'm going to have d over dy of sine star of y times d over dx of y equals 1. And that's going to give me cosine of y, not cosine star, regular plain old cosine, times dy over dx equals 1. And then I'm going to state where I'm restricted to. So if x here is between -1 and 1, right, that means that the sine star of x, the sine star of y was restricted. So I'm going to say note y, because this was sine star, y is in negative pi over 2 pi over 2. Since y was in the output of arcsine. Or a valid input for sine star, either way. Okay. Well, that means dy over dx equals dy over dx. It's not cosine star because I'm taking the derivative of sine, and cosine star has a much different, right? Y is between negative pi over 2 and pi over 2. And cosine star isn't going to help me because it's not defined over negatives. So I need the real cosine here, which I get because the derivative of sine star and sine are the same. It's a good question. But I want this bit of input, so I got to have regular cosine, not cosine star. It's a good question. All right, so what I'm going to get is dy over dx equals 1 over the cosine of y. Now, I just did something. Note, I just lost the endpoints. Right? Because if y equals negative pi over 2, or if y equals pi over 2, cosine of y is 0. All right? Now, I've got dy over dx equals 1 over cosine y. Now I'm going to use something called the triangle trick. Okay. And here's how the triangle trick works. Cosine is adjacent over hypotenuse. Sine is opposite over hypotenuse. Right? SOHCAHTOA. So what I've got is the triangle trick here. Remember that y is an angle. So I'm going to stick that angle right there. Okay? How do we feel about that? 1 to 5. Right? It's the output of arcsine. That means it's an angle. Okay? Now, I know sine of y equals x. So the opposite over the hypotenuse equals x. So I'm going to call the x that by calling the hypotenuse 1. And what I have here is the cosine. Well, the cosine is the adjacent over the hypotenuse, isn't it? That means this is the cosine of y. Now, by the Pythagorean theorem, I've got 1 squared equals cosine of y squared plus x squared. And that means that this is 1. 1 minus x squared equals cosine of y squared, which means that the square root of 1 minus x squared equals cosine of y. Now, why don't I need the plus minus? It's not erasing again. Why is it not erasing? Erase. It's not erasing and it's not selecting. Okay, it's lagging. All right. I'll get rid of that S when I post the thing. Okay, so forget about that S. It won't erase. Okay. Notice y is in negative pi over 2, pi over 2. So cosine of y is greater than 0. So I don't need the plus or minus. I only need the cosine. I only need the positive side. So dy over dx equals 1 over the square root of 1 minus x squared. Are there any questions? Okay, so today we did the algebra of inverses. We did a lot, right? We did all of the algebra of inverses stuff, which is now not showing up because it doesn't apparently want to go back to my outline. the computer is screaming at me that it's had enough. It's been doing algebra all day, and so it's kind of had it. We'll just do this. Okay, so today we went over inverses functions and what it meant for a function to be one-to-one, and then we did the inverse trig functions. We showed this triangle trick, and we actually did the derivative of arcsine. Okay, next time I'll probably I want to finish this up next time. So we'll go ahead and talk about tan, and we'll do a few more examples of this triangle trick tomorrow evening. Some of those things on WebAssign are all about that triangle trick. So practice it, play with it some, and I'll do a few more examples tomorrow before we move on to the stuff that is the proper stuff in Module 3. Yes, this stuff is on Test 3. It really should be on Test 2 just because it's kind of that kind of stuff. Right, because I used implicit differentiation and all that. It's really test 2-ish material, but it's on test 3. And then we will, so I'll finish that stuff up tomorrow. And then we will, we'll finish up, we'll start the shapes of curves stuff and the optimization stuff, which is the core of Module 3. Are there any questions for me? Okay, well, good evening, and I'll see y'all tomorrow, 7 p.m. again, and in class tomorrow, if you'll be there. Have a good evening.